It feels real, that hard, immediate resistance when bone hits wood. But the feeling of physical solidity is a biological lie. Your brain is sealed inside a dark, silent vault of bone, with no direct access to light or matter. It only ever receives abstract electrical signals zipping up your nervous system, and it has to guess what those impulses mean. If we scale down into a single atom of that wooden table, we find a void. An atom is 99.9999999. Evolution didn't wire us to perceive a storm of quantum voids and force fields, because that doesn't help us survive. Instead, waking reality is a controlled hallucination. Your brain paints a user-friendly, solid-feeling interface over that quantum noise to help you navigate the world. To understand how the universe behaves when nobody is looking, physicists use the double-slit experiment. They take a barrier with two thin, parallel slices and fire single particles of light, photons, at it, one by one. Left alone, a single photon acts as an expanding wave of probability. It passes through both slits simultaneously, interfering with itself to create a complex, striped pattern of light and dark bands on the back wall. When we place a detector at the slits to extract which way information, the wave function collapses. The striped pattern disappears, and the photon hits the wall in two simple lines, acting like a solid single marble. Physical reality is not a fixed state. It renders only when it is forced to provide an answer to a measurement. Subatomic particles are fragile. To measure one, you have to physically interact with it, usually by bouncing another photon off it. This interaction causes decoherence. The measuring tool knocks the system out of its delicate wave state. This suggests that the observer's interaction is what changes the outcome. In the delayed choice quantum eraser experiment, scientists pushed this to the limit, waiting until after the photon had passed through the slits before deciding whether to observe it. When the detector gathers the which way data, the wave collapses. However, if researchers scramble or erase that data before a human can read it, the interference wave pattern returns. The physical interaction of the camera is not what solidifies reality. At the smallest scales, the universe is governed by the availability of information. If the data is knowable, you get particles. If you destroy the data, you get waves. This mirrors the lazy loading techniques used in video games. To conserve processing power, game engines don't calculate every texture in a world simultaneously. They only render what the player is looking at. Quantum mechanics suggests a similar optimization, a universe that exists as a vague wave until a measurement forces it to calculate a specific, localized answer. Scientists have moved beyond the theoretical and are now engineering these probability waves into hardware. In trapped ion quantum computers, engineers vaporize metal into a gas and use electromagnetic fields to suspend a single ion in a vacuum. Isolated from the noisy outside world, that atom remains in its uncollapsed wave state. It becomes a qubit. Quantum algorithms then manipulate these waves. They use constructive interference to amplify the correct answer to a calculation, while using destructive interference to perfectly cancel out all the wrong ones. We are learning to program the mathematical probabilities beneath matter. Every chair we sit in or table we touch is just a biological interface. And when you knock on wood, you are forcing a localized collapse of quantum fields to provide data.